Hello and welcome to our next video lesson on stoichiometry. You might find a teacher here or there who would say stoichiometry, but I've always thought that sounded kind of funny, so I say stoichiometry. Reading from your textbook, stoichiometry comes from the Greek words stoichion, meaning element, and metron, meaning measure. Cool, huh? Little history lesson. All right, so what is stoichiometry? Stoichiometry is the study of amounts of products and reactants in chemical reactions. What does that mean? It means that in this chapter, I'm going to be giving you an amount to begin with, and you're going to be predicting how much can be made, how much we need to make that, or I'm going to give you how much we need, and you're going to tell me how much stuff to use to make it. It's just like a recipe. Have you cooked before? I like to cook. I made some really good chocolate chip cookies the other day. Lots of chocolate. A balanced equation is like a recipe for a chemical reaction. It shows how much of each reactant you need to make certain amounts of product. Or you can, again, look at how much product you need and predict how much reactant you need. It works both ways. It's really cool. This is a great chapter. I give it a smiley face because it is so cool. So we're going to start with an analogy. So I don't even want to talk about chemistry to begin with. I want to talk about bicycles. You're the plant manager of a bicycle factory. Congratulations, you're not even in high school and you already have a big important job. Your factory combines wheels with frames. That's wheels with frames. Now, I know that bicycles have lots of parts. Your responsibility, your factory, is just wheels and frames. And you have to manage the resource so production of the bikes doesn't stop. That's very important because if you're not producing bikes, you're not making money. If you're not making money, you are out of a job. See, this would be you. If your plant doesn't make money, you would be out of a job. Okay, so here is our chemical reaction. This is a wheel, okay? And this is a frame, and this is a completed bicycle. Now, let's balance this equation. How many wheels per frame do we need to make a bicycle? Did you say 2 wheels per frame? If you did, that is correct, 2 wheels per frame. We could even make it a chemical equation. We could say 2W plus 1F. I'm not going to write the 1 there, understood? Equals, did you say W2F? Isn't that neato? That's just like chemistry, but we're talking about a bicycle. Okay, now you're the plant manager. What happens if there's a sale down the street at the wheel factory and you get to buy at reduced price, you get 100 wheels? Can you predict how many frames you would need? Did you think 50 frames? How do you get that? How do you get 50 frames? Well, you should see that for every 2 wheels, we need 1 frame. So if you have 100 wheels, you need 50 frames. It's a ratio, which is all that we're doing in this chapter. It's just a whole bunch of ratios. Now, how many bikes could you make from that? Well, there are 2 ways to look at it. You can look at the ratio between wheels and bikes, or you can look at the relationship between frames and bikes. For every 1 frame, remember there's an imaginary 1 here, for every 1 frame, I can make 1 bike. So if I have 50 frames, I can make 50 bikes. Nice job. You're thinking, that's pretty easy. And you're right, boys and girls. It is easy. Now, let's say the head of your company says, quickly, sir or ma'am, depending on your gender, we need 1,000 bikes by Wednesday. You quickly run, and how many frames do you order? Think. Look at the ratio. For every 1 bike, there's 1 frame, so you should order 1,000 frames. Now, for every 1 bike, there's 2 wheels, so what's the answer? Did you say 2,000 wheels? If you said 2,000 wheels, that's correct. It's just a ratio. Now, let's say there's a sale on wheels and frames, and so you buy 50 wheels and, making this number up off the top of my head, 10 frames. How many bikes can you make now? Well, what you should see is that these are not at an ideal ratio. The ideal ratio was 2 to 1, and this is 50 divided by 10 is a 5 to 1 ratio. So you should be thinking to yourself, we're going to run out of something first. I'm not sure which. Let's see. Okay, so if we have 50 wheels, we can make 25 bikes. I'm just going to put a 25 right here to remind me how many bikes we can make. If we have 10 frames, how many bikes could we make? Well, we can make 10 bikes. Now, think about that. Could you actually make 25 bicycles with what you have? If the answer is no, you are correct. You cannot, because you would run out of frames. Once you've made 10 bikes, you would run out of frames. So the maximum number of bikes we can make is 10. And so we would use 10 frames, so I'm going to subtract 10, and we would have 0 frames left over. Now, how many wheels would we use? We started with 50 wheels. If we use, let me change color. If we're going to make 10 bikes, that means we would use 20 wheels. And how many wheels would we have left over? Did you say 30 wheels? That's correct. So what you should see here is that we have an interesting situation where we're not at an ideal ratio. Example 1 and 2 were ideal ratios. Example 3 is a non-ideal ratio. Now that allows us to introduce 2 new terms. New term number 1, the reactant that runs out first is called the limiting reactant. Limiting reactant. The reactant that gets used up or runs out first is called the limiting reactant. I'm going to write runs out first. Why is it called the limiting reactant? It controls the reaction. It controls the reaction. Did you notice that once we ran out of frames, we could make no more bicycles? So once you run out of limiting reactant, the reaction stops. That's an important idea, so write that down, even though I didn't write it. Once you run out of limiting reactant, the reactant stops. The reaction stops. Now, wheels over here, we had lots of wheels, so we call this our excess reactant, which I like to abbreviate XS. I know, that's cool. Almost like the band In Excess. That was from my day. What is the definition of excess reactant? That means we do not run out of this reactant. We have extra left over. I'm going to just write the word extra. Oh, look at that funny abbreviation. I left out an E. That saved me like a second. So the excess, we have extra. We don't run out of that. All right, checking time.